Evet, aradan önceki son konuşmacımız Grundfos'tan Dermott. Kendisini alkışlarınızla sahneye davet ediyorum.
Good afternoon, everybody. I'll introduce myself very briefly. Liam is my name. I'm part of the Grundfos Global Sales Development Team. And I'm delighted to be here in Istanbul this morning, or this afternoon, to give you a little bit of an insight on distributed pumping, which is probably just a slightly different way of pushing chilled water or cooling water around a data center or whatever application it might be. So I'll tell you a little bit about Grundfos, tiny bit about sustainability, which is really important to us, and then I'll go through distributed pumping with you. I think probably about 15 minutes or so, and then we'll have you in there for lunch. So a little bit about Grundfos. We're a Danish pump or water solutions company. We were founded in 1945. We've got about 20,000 employees. We're privately owned. We've a turnover of about $5 billion. And as I said, privately owned. We reinvest 5% of our turnover back into R&D. So it gives us a good investment in R&D. And we're probably one of the world's biggest pump solution companies. When we look at sustainability, which is very, very important to us, we work mainly on energy savings, water savings, providing water or access to water for people, particularly in need, and the circular economy. Circular is really, really important to us. We produce our sustainability report every year, so if you really want to find out about it, have a look at grundfos.com and you can find all the information. But our targets for the next few years are, by 2030, to reduce Scope 1 and 2 by 50% and Scope 3 by 25%. And then by 2050, Scope 1, 2 and 3 by 90%. And we're well on target to do that. And if we have a look at data center cooling or cooling in data centers, I don't have to go through. I think probably most of you will understand where we're going. We're generating more and more data. We need to work on more and more data. And because of that, we need to find more economic, better ways to do cooling. And the aspect that we're looking at certainly is the pumping of the water. So if we look at distributed pumping and how we get water around a data center or any other type of cooling application, basically we've got a chiller plant and we have valves which are opening and closing, and those valves are controlling the amount of cooling we got going to the different applications. And the difference that we would like to look at with distributed pumping is, instead of opening and closing valves which cause a lot of energy, there's friction losses and we need more energy to get across those valves, we look at using smart, intelligent pumps. And those pumps have various variable speed drives built in. Taking out the valves, we reduce the friction loss in the system, so we need less energy to pump the liquid around. And we also balance the secondary and the primary sides, and I'll go through how we do that now. So if we look at distributed pumping and how we organize the system, it's a more simplified design process. We decouple. So we use the decoupling line here between the primary and the secondary, which is really, really important. We would like to have no flow in this decoupling line all the time, but there are times when we do. It lends itself very much to modular design because we're putting pumps at the point of application. So if we want to put another cooling load in, we just put another set of pumps in with it. And it makes it very, very easy to balance. And we get very involved in the whole design of this system. So we will work with designers, end users, installers to make sure that it's designed to meet the needs. And some of the other benefits, as I mentioned, it reduces the energy consumption on the pumping plant. So all of these pumps here will use less energy than a standard design of a pump or pump system, we would estimate that in a lot of cases we can get up to 50% energy savings on the pumping plant. And we can also affect energy savings on the chiller plant as well, because we balance the system, we get the system very, very well balanced. As I said, we balance the primary and secondary, and we optimize the delta T. So whatever the delta T is designed for, we keep it at that. We won't have low delta T syndrome, and that gives us efficiency on the whole cooling system. And that efficiency, we've measured in some cases, and it can be up to about 14-15% on the cooling load, which is substantial. And as I mentioned, modular design is very, 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 very workable with modular systems. So if we had a look at a system and we've a lot of small loads, or for some reason we can't use a full distributed system, we can look at zone distributed systems where we take groups of cooling loads, and we're showing liquid cooling here, immersion cooling. It could be fan walls, or it could be crawl units or whatever, and we would group them together, particularly if they're small loads, and we would put a pumping system in then to distribute to them. It will, at that stage, we're using valves again, but we're not using as many valves in the system, so we're not getting the full energy savings we get with a complete distributed pumping system, but it's a halfway point for people who can't or don't want to use a full distributed pumping system. And I'll go through how it works and how we balance the systems now. So as I mentioned, we use this decoupling line, and the ideal situation, we won't have any flow in the decoupling line when the system is fully balanced. If we need to pump more than the load, the minimum load is, then we'll circulate water through the decoupling line to save the system. And we control the primary pumps based on what's happening on the secondary side. The primary pumps, the whole idea of the primary side is to provide just enough cooling water to meet the secondary loads. Each secondary load will have a pump on the system, and that pump will be connected to a sensor or BMS or whatever, and it will regulate flow to the cooling load in accordance with what that demand is. So we're all the time monitoring that and providing just enough cooling for the actual load, and then we're sensing this on the primary pumps and meeting the complete load. And I'll go through how we do that now in a second. So the ideal situation is we're generating chilled water, we're pumping it out to the secondary side, we don't have flow in the decoupling line. And when we do this, the primary pumps will come down in size, so they won't be as big as the primary pumps you would see on a standard pumping system, because we got our pumps out on the secondary side, which are taking up most of the friction losses. The primary pumps literally have to get it out to the decoupling line and back, and the other pumps will take the load from there on. If we have parts of the system shutting down, each pump will then take over and provide the load for its cooling load, regardless of what else is going on in the system. So it's autonomous really to its own load. And we optimize the balance between the primary and secondary sides. And as I mentioned, the delta T, and I'll show you how in a moment we manage that delta T. So if we look at the secondary side, as I said, there's a pump on each load, which is providing the right amount of cooling. And we can see here where we've got a zoned load where we've got one pump pumping up to various different loads. And we can mix and match different kinds of cooling. So we can have fan walls, we can have crawl units, we can have liquid cooling, all on the system. It doesn't really matter to the individual pumps what the load is. They're getting a sensor feedback and they're reacting to what's going on. And we're constantly monitoring what's going on in the system and constantly reacting to any changes in that system. And that goes through the life of the whole pumping system. As we might get some build-up in some of the pipes or whatever, the pumps will see that and they will react in accordance with what's going on. So they're constantly looking at the load and meeting that demand. And if we want to put extra onto the system, as you can see, we put on a new load and we put pumps on that load as well. The primary pumps obviously have to be sized to meet that full load, but we can look at that through design phase or add on in a modular way. We can add on to the primary load as well. And how we balance the primary and secondary side then, if we look at the primary, the first thing that we do is we use a controller. We call it an MPC controller. It's a standard controller that we use in all our HVAC applications, so there's nothing strange about this. The pumps themselves are standard pumps. They're just worked in a slightly different way. When we have a load come on, the chiller will come on and we will check the flow rate across the circuit through differential pressure sensors. So if the demand is less than the minimum flow of the chiller, we'll make those chillers, or we'll make sure that we have the minimum flow going through the chiller. And in that case, we will have flow in the decoupling line, but it means that the chiller is saved and we don't end up destroying the chiller. Once that minimum flow is met, we start looking at what's going on the secondary side, and we speed up and slow down the primary pumps to meet the demand on the secondary side. And this gives us a very, very balanced system. And as I said, we're doing this in real time. It's constantly going on. We're constantly looking at the minimum flow to make sure we've got that, and then meeting the flow that's happening on the secondary side. And how we link the two systems is quite simple. We put temperature sensors across the decoupling line. T1 should equal T2 and T3 should equal T4. And if that's the case, we have the system in complete balance. We're generating enough liquid to our cooling on the primary side to meet the demand on the secondary side. If the load changes on the secondary side, we will get changes here and the pumps will speed up and slow down to bring it back to equilibrium. And as I said, this is happening in real time all the time. We have a demo system in one of our plants in Singapore, and I've played around with it. And when we manipulate and change some of the temperatures, it comes back into sync within probably about half a minute or so. So it's reacting pretty quickly. And as I said, they're standard temperature sensors, standard controls, standard pumps. Everything is standard in this system. It's just organized in a slightly different way. So the idea is we have no flow in the bypass or the decoupling line. And that optimizes the whole energy consumption on the system. This has been looked at. ASHRAE did a paper on this about 30 years ago, and they looked at distributed pumping and different forms of distributed pumping, and it just hasn't really been commercialized. Grundfos, we've been doing this now for the past 5 years or so in a lot of different applications, and the last couple of years we brought it into the data center world. So if we have a look at this system here, it's completely in balance, and we won't have flow here. We're generating enough cooling for the secondary side. Over here, it's gone out of balance. We can see we have 11 degrees up here. So we're under pumping. We're recirculating through the decoupling line. We will speed up the primary pumps to meet that demand. And the opposite's happening over here. We're over pumping, and in this situation, we slow down the pumps, and it'll happen very, very quickly, and constantly we will be doing this. So a very, very simple way of doing something that might look a little bit complicated, keeping those two systems in balance. And as I said, it works very, very quickly. So if you look at the sequencing and security, which is really, really important, we make sure that we meet the minimum flow of the chiller. And after that, we start looking at what the load is on the secondary side and meet that load. So it's happening constantly in real time. And as the system is operating, this constantly happens. Now we do rotate the pumps, we do different things like that as well, so we're not having the one pump running all the time, or we have our redundancy built in, but we just keep that system running as efficiently as possible. And if we look at different loads, as I mentioned, we can use this with hybrid cooling systems where we have a mixture of air and water or liquid cooling. We have different applications down here on different levels, and we have a pump or 2 pumps as a standby, which is meeting the load on each of these applications. We've got different ways of doing redundancy. We can see we've looked at twin pumps here, or we've got a valve arrangement here. We don't have redundancy on this one, whereas over here we've got some CDUs and we've got redundancy built into the CDUs. So we've one redundant CDU for the rack system. And the CDUs will generally have twin pumps in them. That's the way they're been designed and manufactured. If we look at fan walls and craw units, we'll generally have N+1 or N+2. So we've met our redundancy on that way as well. It's built into the whole system. Or we can go for zoning as well, where we've got twin pumps meeting a complete zone. So there's lots and lots of different ways that we can design a system. There's lots of different ways we can have it installed to meet whatever levels of redundancy are needed. And this is all connected to the BMS, so you've got feedback all the time through Modbus or Profibus or whatever the BMS system is that's been used. So if we just recap, we balance the primary and secondary circuits. We use pumps instead of valves, so we don't need to generate as much pressure to overcome the resistance across a valve, and that's energy saving. We put non-return valves on the system so that we don't get backflow if parts of the system are switched off, and less friction in the system, less energy required to pump across it. And as I mentioned, we will sit down and we will go through a project with the designers and hand over a complete design package so that it can be checked and verified and made sure that everything is as people want it. And part of that will be energy savings. We can work out what the energy savings or the proposed energy savings should be on a system and document all of that. And then afterwards we can record, measure, and report back on it as well through BMS systems. And if we have a look at the products that are being used, they're standard Grundfos products, which are available in the market all the time. The controllers are standard, the pumps are standard, the sensors are standard, and the communication cards are pretty standard as well. So nothing here is unique. It's not something that cannot be picked up through standard distribution. And we can make the pump skids on the primary side, we can modularize them and have them come in as skids and kits and whatever. So it's all pretty standard Grundfos product, just used in a slightly different way in how we control it. And if we look at a case study, and this is in this region where we've had 10 large primary pumps, N+2, and we've replaced them with a number of 10 primary pumps which are smaller. So we've gone from 30 kilowatt down to 11 kilowatt, and then quite a lot of secondary pumps, which are quite small pumps as well. The energy savings in this case turned out to be almost 400,000 kilowatt hours. And as we go up bigger in systems, and as we go to systems which have more diversity on them, you're going to see more and more energy savings as well. And what we're not measuring and what we're not showing here is the efficiency on the chilled water system. And as I mentioned, we've measured this in some places and we're getting up to 14, 15% on the overall chilled water system because it's fully balanced. So there's huge energy savings to be made. It's modular, which makes it easy to build a system. If it's a colo or whatever and you're getting clients in over time, we can make it work very efficiently from day one right up to when the full load is on the system. Or if it's a system where we plan for expansion in the future, once again it lends itself to that modularity. So that, I think I stuck to more or less the time. I have 25 seconds left. If you would like to talk to us about this, we have a stand inside, and we've a lot of local people here as well who would be delighted to talk to you and maybe have a look at some projects if they are coming up and see if it's a viable system which could be worth using. So thanks very much everybody for your time, and yeah, I think we're done.
Evet, 2'yi 5 geçe görüşmek üzere. Yalnız şöyle bir şey var. Masa, sandalye düzenleri değişecek. Çantalarınızı yanınızda alırsanız, çantalarınızı, poşetlerinizi vesaire iyi olur sizin için. Afiyet olsun.